We are now at part 2 of lecture 8 of Applied Machine Learning. In this video, I am now going to focus on the main topic of this lecture, which is the naive Bayes algorithm. In the previous video, I defined the problem of text classification, which is going to be a motivating problem for the naive Bayes algorithm. And now in this video, I'm going to start defining what this algorithm is. I'm going to start by, again, defining the model that naive Bayes is optimizing, and then I will talk about how we can learn this model in the next slide, in the next video. So recall that our motivating problem is text classification. This is an instance of a classification problem in which we are trying to, in which X is a sequence of words or a sequence of characters, which can be of arbitrary length and of high dimensionality. And we want to classify this X. And practical examples of this problem include spam filtering, fraud detection, medical record classification, and others. And we saw in the earlier video that one of the main challenges of applying machine learning algorithms to this data set is how can we featureize this input X in a way that works with the algorithms that we have seen so far. And the approach that we have proposed is something that is called bag of words feature representation, which just means that given an input X, we have some vocabulary V, which is a set of words that we're going to consider. And then the feature representation of X is a long vector with one component per word, and at that component we have either a 0 or a 1, depending on whether we find this word in X or not. So here here we have 0 at the first index because the word church is not found in X. We have 1 at the second index, for the one for the word doctor, because doctor is found in this input X. So this is our definition of bag of words feature representation. Now, we would like to apply supervised learning algorithms to this problem, and we have seen two kinds of supervised learning algorithms. We have seen discriminative models, which is an example of a discriminative model would be logistic regression, and then we also saw generative models, of which an example would be Gaussian discriminant analysis. And these differ in whether they model the full distribution of X and Y, or whether they're only modeling the conditional distribution of Y given X. And the idea of generative models is, instead of simply predicting the class, we learn a model of how the data points X, of how the inputs X look like, and then when we have to make a prediction, when we have a new data point X prime, we have one model of X per class, and we report the class under which our data point has the highest probability. And mathematically, this can be defined by the following equation. An example of generative model is Gaussian discriminant analysis. In Gaussian discriminant analysis, we assume that the conditional probability of X given Y is a multivariate Gaussian, also known as a normal distribution, with parameters mu and sigma. And the distribution over classes is a categorical distribution, which means that we have k possible classes. Each one has a probability phi, and the probability of seeing class k equals phi. So this defines a joint model over X and Y as follows. Here we have a formula for a probability of Y equals k, and we have a probability of for X given Y equals k. This is our Gaussian, this is our categorical, and the resulting joint probability over X and Y has the following form, and we call this a mixture of Gaussians. So this is a Gaussian discriminant model, and it is a really important algorithm in machine learning. What would happen if we were to apply this algorithm to the text classification problem that we saw earlier? Well, the first problem that we immediately see is that our data, which follows a bag of words representation, is discrete. And the JDA model, the GDA model, uses, it assumes that the data is following a normal distribution. And so clearly this model is misspecified. We saw a similar instance of this problem when we talked about whether we can apply linear regression to a classification problem. In principle, we could fit a Gaussian to this binary data, but it would just be wrong conceptually. It would not be an elegant approach. And in the same way that logistic regression, in the same way that linear regression does not work as well as logistic regression on a classification problem, in the same way, a specialized algorithm that takes into account the fact that these variables are all binary, this specialized algorithm will work better on this data set. So this is our first problem. So we can try to resolve this problem by, instead of assuming that the conditional distribution is Gaussian, we could assume that it's categorical. So recall that a categorical distribution is just a generalization of the Bernoulli to k classes. In other words, we have some number of outcomes, and let's say we have m different outcomes. A categorical distribution will assign a probability to each of these m possible outcomes. So for example, if we're throwing a die and it has 6 possible outcomes, there's going to be a probability assigned to each of these 6 possible outcomes. If we apply the categorical distribution to this particular example, we are essentially going to have to define a probability for each possible x. And x here is going to be our, so I should have specified that x is it's a featurized version of the input text. So it has a bag of words representation, which means that it has, it's this binary vector. And we have to specify a probability for each possible input. And so if we have a categorical distribution, then we have to specify a probability for each possible assignment of 0 and 1s to all the components of this vector. So we have to assign a probability to 1, 0, 0, 0, to 0, 1, 0, 0, 0, and so basically every possible assignment of 0 and 1s to these components, we have to assign a probability to it. So here in this example, I'm assuming that the categorical distribution says that the probability of this particular sequence of words with their binary indicators, it has this value. Now, this also has a problem in that if the dimensionality of our vector is really large, so imagine that we have a vocabulary of 10,000 words, then the number of possible values that x can take is 2 to the power 10,000, which is a really big number. And so in order to model this x using a categorical distribution, we need some way of specifying essentially 2 to the 10,000 possible probabilities, which is going to be really complicated. It's going to be really hard to enumerate and to assign a value to all of these numbers. For example, so in other words, this categorical distribution would have 2 to the power d minus 1 parameters, and we would have to specify all of these parameters. And with a number that's this large, this will not even fit in the memory of our computer. So we cannot really model this this type of input as a categorical. We need to be a little bit more clever. So the naive Bayes algorithm, it makes a particular assumption that simplifies this problem and resolves this high dimensionality problem that I just defined. And the particular assumption that it makes is also called the naive Bayes assumption, and it goes as follows. In order to deal with these high dimensional x's, we are going to assume that the distribution of x given y factorizes in this form. So what this means is that the probability of having a particular x given a y is simply a product of probabilities it's a product of d probabilities, and each of them is simply the probability of one component given y, and this is independent of all the other components. So what it means is that the probability of seeing word 1 given y and word 2 given y, this is just a probability of seeing word 1 given y, and it's independent of whatever value word 2 takes, right? So in our earlier example here, we had to assign a probability for when we have 0 here and 1 here, and if we have 1 and 0 and 0, 0 and 1, 1, just over these two dimensions, we have 4 possible values that we can take. And if we're using the naive Bayes assumption, then the probability of having 0 here is going to be the same regardless of whether we have a 1 or a 0 at the second position. So this is called the naive Bayes assumption, and it's a really important assumption that's used in many applications of machine learning, and typically these kinds of algorithms that use this assumption are called variants of naive Bayes. So here, let me give you again a more specific example. Let's say that X has a binary bag of words representation. Then the probability of the jth component given y is simply the probability of seeing the jth word. And because X sub j is binary, we can model this probability as a Bernoulli. And the Bernoulli only has one parameter. It has the probability of seeing the word, and 1 minus that is the probability of not seeing the word. So we only have one parameter now for each of these distributions. And so now if we look at the full distribution, that is the product of d Bernoulli distributions, well, now we only need d parameters instead of 2 to the d minus 1 to specify this distribution of x given y. So this is a really big simplification of the problem. Here we're using a number of parameters that is very small, very tractable, and we can scale this algorithm to really high dimensions, such as a very large vocabulary size. So this algorithm is going to be really scalable and is going to be applicable to our text classification problem. Now, of course, we are making a lot of simplifications because words are typically not independent. So, for example, if we have the word doctor, well, probably we'll also have the word patient, or maybe disease, or maybe medicine, or hospital. These words are clearly correlated. So here we're making a big simplifying assumption. However, we'll see that in practice, this is not that bad, and these kinds of algorithms, they actually have really good empirical performance. And now, using this using this naive Bayes assumption, I can define the naive Bayes. I can start defining the naive Bayes algorithm, and I'm going to first specify the model that this algorithm will take. So if you recall, a supervised learning algorithm is comprised of a model, an objective, and an optimization procedure. And here I'm defining the model for the naive Bayes algorithm. And this is going to be a particular type of model called the Bernoulli naive Bayes model. And it goes as follows. First, at a high level, we're going to take the same strategy as we used to define the Gaussian discriminant analysis algorithm. We're going to define a probability over the y's, and then we're going to define a probability of x given y. And our probability over the y's is going to be the same as we had earlier. It's going to be a categorical distribution. So this first part is the same as in Gaussian discriminant analysis. And now for the conditional probability, instead of making it a Gaussian as it was in the Gaussian discriminant analysis algorithm, now this is going to be the following expression, which is a product of Bernoulli distributions. And we have used the naive Bayes assumption here because the probability of each component of x is independent of all the other components. So here again, each distribution, each conditional probability of x given y is a product of d Bernoulli distributions, where each distributions assigns a probability to the event of seeing a particular word at its location. So here, the probability of seeing a sequence of words where we have 0, 1, 0, 1 is the probability of seeing 0 given the class times the probability of seeing 1 given the class, etc. So this is the functional form of our model. And I can define it as follows. This is a slightly more, this is just specifying the same thing. It's a mathematical form, and the categorical distribution has these parameters phi, and each Bernoulli distribution has one parameter called psi. And so here now we have a number of parameters that is approximately k times d, which is something that's manageable. So this is the definition of the Bernoulli model, and in the next video I'm going to show you how we can learn this model from data.